Here we are on a brand new chapter, chapter number 3, and we're talking about polynomial functions. Okay, so we've talked about polynomials in the past. What exactly is a polynomial? A polynomial function. It is a function where you can put it in this form. Now, it doesn't have to be f of x, but we tend to like f because it's the first letter of a function. So this part could be different. It could say y, it could say g of x, it could be any letter like that. On the right, a and n are going to be one letter. Okay, depending on the polynomial, x is your variable. Well, let's talk about these. N needs to be a whole number. So remember what a whole number is. A whole number is, I'll use the curly bracket to show that I'm talking about a set. It can be 0, it can be 1, it can be 2, 3, and so on. It has to be one of those numbers. It can't be anything in between. So if I put a little arrow here, nothing in between. So, for example here, I can have an n. The first one could be a 1, it could be a 2, but it could not be a 1.5. That's the power here. So the first power is n, the second power is n minus 1. So you're going to see that we've put this into a descending order. N minus 3, so now in this example it gets down to 2, gets down to 1. We could actually call this one x to the 0, but usually we don't leave that. So this is set up, the polynomial is set up in decreasing order. So if we look at our examples down here, you can see how this is done in decreasing order. This is an exponent 2, this is exponent 1, and there's our constant term. So that's the first part. The second one is that in this definition, x is a variable. We don't have to use x, but we usually do. So x is a variable, and then a subscript n and a subscript 0 are real numbers. Okay, so when we're talking about real numbers, square root of 2 is okay, that's real, pi is okay, things like that. Okay, so n has to be a whole number, but the coefficients in front have to be real numbers. So in our example here, this 3 is the first coefficient, is that a to the power of n, or a subscript n. It's the coefficient in front of the first term. N would be equal to 1 in this example, and our last term a to the 0 is negative 5. So here's the coefficient of 1, 3, and negative 17, and so on. So those are all examples of polynomials. They all work. Well, let's do a little bit of a vocabulary here. So when we're talking about end behavior of a graph, so end behavior is, well, if I go and draw, the graph, and I recall the way that we use Roman numerals for the quadrants. When I draw a graph, let's say I draw this first one, this 3x minus 5. 3x minus 5 would kind of be a straight line. It would look like this. The end behavior is what happens when x gets exceedingly large. So in y is equal to 3x minus 5. When I start putting in very, very large values for x, what happens to the function? Does it go up or does it go down? Right? So that's really what we're talking about for the end behavior. We're talking about the shape of the graph at the ends. So as x approaches positive infinity, as it gets very large, and also as it approaches negative infinity at the other direction. So in this example here, I would say that y is equal to 3x minus 5. If I was asked what is the end behavior, I'd say it's going up in quadrant number 1, and it's going down in quadrant number 3. So that's a nice easy way to talk about. So end behavior, so we say, does it go up or down to the right and to the left? Does that make sense? So if it goes up to the right, it goes up to quadrant 1. If it goes down to the right, it will be going down to quadrant number 4. And by the way, just a little heads up, how this works is it depends, this whole end behavior depends on two things, the degree, which we're going to be defining next, and the leading coefficient. And in fact, it's just the sign of the leading coefficient. So it depends on those two things that we're going to see that very shortly. It's sort of a nice shortcut that we can take to figure out the shape of a graph. The second one, well, what is degree? So degree is the greatest exponent of x. So this one here would be degree 1. This one would be degree 2. H of x, degree 3. Y of x, degree 5. Pretty straightforward. It's pretty easy when they put it, I'll just clean up a little bit. It's nice when they put it into descending order. Okay, so watch out for a trick. You know, if they might say y is equal to x squared minus 3x to the 4th, because in this case the degree would be 4. So if it's already in descending order, you can just look at the first term. So it's fairly easy that way. The constant term. The constant term is when we're doing in descending order, it's the last one. It's easy to tell because it does not have an x. And by the way, you can think of it as a vertical translation. We know that. And the other thing is, it will be the y-intercept. So looking at our examples, this is a constant term of minus 5. Here's a constant of minus 17, constant of minus 2, and a constant of minus 1. All negative in those cases. The last one, the coefficient. Well, it's our a subscript n. So the leading coefficient, in the first one, it's positive 3. Here it's 1, here it's 1, and here it's 1. So leading when they have it already in descending order. For this one, here my tricky example, the leading coefficient would be equal to minus 3. So it's the coefficient of the term with the largest exponent. Coefficient of term with largest exponent of x. All right. Moving on to the next page, it says here, identify the functions that are not polynomials and state why. Did we get a definition here? So here are the three things to watch out for. It says n needs to be a whole number, there needs to be a variable, and these coefficients need to be real numbers. So looking at our first one, is this a polynomial? The answer is no, it is not a polynomial. Why is that? Well, looking at that square root of x, you're kind of going, what's up with that square root? We don't see that very often. One way to say the square root of x, another way to write it, is to say x to the power of 1/2 plus 5. So here's another way to write that. And then it becomes very clear that the exponent is not a whole number. Whole number. Little shorthand there. Okay, how about the second one here? Y is equal to the absolute value of x. Well, again, and just remember what this looks like. Absolute value of x, the graph is going to look like this. There's no way that we can put this into our exponential form, in our polynomial form. We can't write this as y is equal to a to the n of x to the power of n plus, and so on. We can't really put it into that form. Okay, so we're going to say no, can't be written as a polynomial. This last one, 3x to the 4th. Yep, sounds good. Now what are the things we're supposed to do? We're supposed to say State the degree. So the degree for here, any guess? The degree is 4. It's the exponent. The second thing we're supposed to say is, what is the leading coefficient? The leading coefficient is a 3. And the constant term. There is no constant written, so it is a 0. Okay, how about the letter Y? Sure, that looks like it is. I'll put it as blue again. Yes, I'll even give it an exclamation mark. And so the degree here is 3. The leading coefficient is 2. The constant is -1. All right, I'm going to give you a minute here to do the A, B, C, and D of your turn. So once again, you should either say no, it is not a polynomial function, or you should say yes, it is. And when you say yes, state what the degree, the leading coefficient, and the constant term are. All right, you go ahead, and then I'll show you some nice answers. All right, so here are my answers for that. For the first one, 1 over x. Another way of writing that is x to the -1, which makes it very obvious then that no, it is not a polynomial function because the exponent is not a whole number. It's a negative value, and whole numbers start at 0 and then 1 and then 2 and so on. For the second one, sure, yes it is, although we were sneaky. I wonder if you caught it. The degree is not 2, it's 5, because there's a 5 there. The leading coefficient is -2, the constant is 4. For C, yes, it's a straightforward one. And then for the last one, again, the exponent must be a whole number, so no, it is not. Well, let's take a look here at this next page. Characteristics of polynomial functions. So the first thing that I want to point out to you are the names of the different polynomial functions. So I think we're quite familiar with the term linear and quadratic. So linear is when the term is, when the degree is 1. And here we've got quadratic. I'll get my highlighter here. So here's quadratic. We've got a bunch of quadratics. So quadratic is when it's of degree 2. So you'll notice that all of these is x squared or minus x squared. And then cubic. Here's cubic. What's the degree for cubic? Cubic is when it's of degree 3. Degree 4 is now called quartic. So you see that. Those are all degree 4. And then degree 5 is quintic. Okay, so just a little bit of English. And again, degree 1 is linear. Linear is pretty easy to understand because it's a straight line. Well, what we're supposed to do here is study these graphs and generalize the end behavior of the even degree polynomials. So the end behavior, again, does it go up or does it go down as x gets exceedingly large? So as x here approaches positive infinity, as it gets larger and larger, x squared, that number is going to get squared, so my f of x is going to get exceedingly large. So we could say this is goes up in quadrant 1, and this one here is going to be going up in quadrant number 2. Where else does that happen? Well, that happens for x squared, it happens for x to the 4th. Here's another quadratic term, x squared minus x plus 6. Here's another quartic one, x to the 4th, where it also goes up and goes up. So it seems to me that whenever the leading coefficient is positive, then it's going to be going up in the first and up in the second. So in all these terms, so let's just see all the times where it goes up in the first and up in the second. These are all these different examples, and you'll notice that the leading term, the leading coefficient is positive here. In fact, it's always 1. What about if we have the leading term negative? Well, we know about minus x squared, so then here we could say this goes down in the 4th quadrant, and this also goes down in quadrant number 3. Kind of makes sense if there's a negative sign there. As x gets exceedingly large, goes to the right. Minus x squared becomes a very large negative number. And similarly, as we make x go towards negative infinity, this part here will make it positive, the squaring, and then the negative out front will make it negative again, so it goes down in this direction. Okay, so here we've got the down, and these are all the examples here of it going down. So whenever the leading coefficient is negative, and these are all the even degree. So by even degree, it's either 2 or 4. It's either quadratic or quartic. So we have a bit of a pattern here. So in an even degree polynomial, it's going to be going either both up or both down. And if the leading coefficient is positive, they're both going up. If the leading coefficient is negative, then they're both going down. So that's for the even degree polynomials. Now let's look for the odd degree polynomials, the linear and the cubic. When my leading coefficient is positive, here then we have our up in quadrant number 1 and down in quadrant number 3. So this happens when the leading coefficient is positive. Again, down here, even if it's cubic, we're still getting the up in quadrant 1 and down in quadrant 3 when the leading coefficient is positive. Going over to quintic, again we have that same pattern, and whenever it's negative now, if the leading coefficient is negative, then it's switched, right? Then it's going to be down in quadrant number 4 and up in quadrant number 2. So hopefully that will make a little bit of sense. Maybe on the side we could do a kind of write out what we'd sort of discovered. So if we have an even degree and we have a positive leading coefficient, what happens? It goes up. I guess the simplest way of writing this here is to kind of going something like that. It goes up in quadrant number 1 and up in quadrant number 2. Next, if it's an even degree and a negative leading coefficient, then the easiest way of writing it is something like this, where it goes down in quadrant number 4 and down in quadrant number 3. In either case, it's going to be going the same for all the even degrees. Either they're both going up or they're both going down. Even in the complicated ones like this, right? Even when you get the higher degree. Okay, so now let's go to the next part here. How did I write this? If odd degree now. Oops. If odd degree. Now there's again two options, the positive leading coefficient so if it's a positive leading coefficient, it's going to be up here, and maybe some curls or things like that depending on the function, maybe some changes of direction, but it's going to be going up up in quadrant number 1 and down in quadrant number 3. If it has a negative leading coefficient, sort of the opposite version of this, I'll make a sort of a complicated version of it again. Regardless of what happens in the middle, we know the end behavior. It's going to be going down in quadrant number 4 and up in quadrant number 2. Okay, so hopefully that makes some sense. When you think about x getting very large, what happens to the function? On your own, you can take a look at the graphs on page 109 on your text and list any sort of generalizations that you might notice. And we'll go to this next page, and we're going to try to match the following polynomials with its corresponding graph. Okay, so this is a degree 3, so it's an odd one, and it's a positive coefficient. So we're going to see it go up and to the right, and we're going to see it go down over here. Okay, I'm going to also make a little note about how this works when we get a higher degree. So here, note, degree n has 1 maximum n number of legs. Let me see what I mean by legs. Here this has 1, 2, 3 legs. Okay. Another way of looking at it is the number of turns, so changes of direction. So this would have 1 turn, 2 turns, or it has a maximum n minus 1 number of turns. So this one here, the 2x cubed minus 4x squared, all that kind of stuff, we know it is going to go up and to the right and down to the left, and it has a maximum of 2 changes of directions or 3 legs. So when we're looking at all these, how many of them go up to the right and down to the left? Actually, only this one, only B does. So I'm going to say that this first one goes with the letter B. How about number 2? It is x to the 4th and it's negative, so that means it's going to be going down to the left and down to the right. And the only one that does that is C, so I'm going to say C for that. For number 3, it's negative and it's odd, so it's going to be going up to the left and down to the right. That looks like it's letter D. And for P, x to the 4th, it's even and it's positive, so it's going to be going up to the left and up to the right, so this would have to be A. Hope that makes sense for you. Okay. In our last page here, it says examples of a polynomial function. Okay, so now this is sort of a more traditional stuff, so we're moving away from the graph and we've just got more of a standard definition or way of looking at polynomials. It says a toaster oven is built in the shape of a rectangular prism. So anytime we've got a prism, you see that word prism, it means that the shapes on the ends are the same, and in this case the shape on the ends is a rectangle. So if I draw a rectangle and then I say okay, a prism, so I just turn that into a 3D shape, kind of like that. So the fact that it's a rectangular prism means that this side here and that side there are the same shape and same size. Okay, so it's a rectangular and then just given a three-dimensional shape added onto it. Its volume V in cubic inches is related to the height by this function here. What is the volume in cubic inches of the toaster oven if the door height is 8 inches? So really all we're doing is we're finding V of 8. So we're plugging in an 8 wherever we see the h. So it's going to be 8 cubed plus 10 times 8 squared, here I'll put parentheses maybe, plus 31 times 8 plus 30. When we get our calculator out, I'm not even sure, I haven't figured that one out. Maybe I'll come back to it. Okay, I did pause and I just came back, and using my calculator I get 1,430. I got to be careful now about my units. It says what is the volume in cubic inches, so then I'll write inches cubed, because volume is going to be measured in cubic units. Pretty well, just plug and play that kind of question. Example number 2 says a bank vault is built in the shape of a rectangular prism. Its volume V is related to the width W in meters of the vault doorway by this function here. What is the volume in cubic meters of the vault if the door is 1 meter wide? So again, very easy. V at 1 is going to be equal to 1 cubed plus 13 times 1 squared plus 54 times 1 plus 72. And that one will be 140. And the units will be meters cubed. There's the answer. And then it says, what is the least volume of the vault? What is the least volume of the vault? Well, can we put any number we can into this function? So again, like, what does this mean? When we do a function notation, we called it v, didn't we? So if I call this function v, what we're doing is we're putting a number into it. And in this case, we're calling it w. And then what comes out is the v at w. It's kind of like this is the x, and this is the y that comes out. We can't put anything we want into this function because it only works for certain range of values, for a certain domain. What is the least volume that could come out? Can we have a negative volume of a vault? No, we can't. So I have to say the least that can come out of this would be 0. What is the width of the door for this volume? So in other words, if we said that w is equal to 0, that's the least volume, then w is equal to what? What would be the width of the door? So going back to our function here, we would say v at 0 is equal to, well, if we plug in, oh, actually the least volume would be, I looked at that wrong. I don't think we can have a door. Let's look at this differently. The smallest width we could have would be a 0 to go into that function. So instead of looking at it this way, I'm going to say, what happens if I make the door have a 0 width? Then what comes out is 72, because this function here, if I plug in a 0, I'm going to get a 72. So if I make the door 0 meters wide, the volume of the vault, according to that definition, would be 72. So what is the least volume? 72. What is the width of the door for this volume? 0. Is this realistic? No. You really can't have a door that is 0 meters wide. So the whole point of this part is that when we have polynomial functions to represent real-world situations, every once in a while we need to step back and say, what is the domain here? Can we have a negative volume? Can we have a door that's 0? And things like that. Okay, so I'll get you to do these ones for homework, and again, we'll see you in class.